A free energy developer who lives in South Africa and who prefers to remain anonymous has very kindly shared the details of his compact self-powered generator so that you can build one if you choose to do so. The developer has continued developing his device through several versions. An early version of the generator had 4 coils and a rotor which has 5 magnets in it. Very soon the 4 coils were increased to 5, with the additional coil having 3 separate windings. Even if you're not familiar with electronic circuit diagrams, please try to follow along as we run through the circuit diagram and explain how the generator works. This is the basic circuit diagram here. The battery marked A, which is here, powers the circuit. A rotor C contains 5 magnets, and it's moved so that one of the magnets passes near the coils. The coil set B, this is the 3rd coil here on the right, has 3 separate windings on a single core, and the magnet moving past those 3 coils generates a small current in them. The current in coil number 1 flows through the resistor R and into the base of the transistor, causing it to switch on. The power flowing through the transistor coil 2 causes it to become a magnet, and that pushes the rotor disc C on its way, keeping the rotor spinning. It also induces a current in the winding 3, and that current is rectified by the diodes shown in blue and passes back to charge battery A, replacing most of the current drawn from that battery. When the magnet in rotor C passes away from the coils, the transistor switches off, moving its collector voltage very quickly up to the plus 12 volt line, starving coil 2 of current. And because the way that coils work, the coil drags the collector voltage on up, and it would reach 200 volts or more if it were not connected through the red diode to all 5 batteries, which are connected in one long chain. The batteries will have a combined voltage of just over 60 volts, which is why a powerful, fast-acting, high-voltage MJE 13009 transistor is being used. That transistor is also sold under the title T13009. As the collector voltage passes the voltage of the battery chain, the red diode starts conducting, passing the available energy in the coil into the battery chain. It also draws in current from the surrounding local environment energy field, and it's that outside current that really charges the batteries and powers the entire circuit. The current pulse passes through all 5 batteries, charging all of them. The result is an output of 40 watts of mains voltage and frequency, 2 12-volt batteries maintained fully charged, and 3 additional 12-volt batteries charged up for later use. Loosely speaking, that is the basic generator design. In the prototype, the load for long-term testing was a 12-volt 150-watt inverter, which was powering a 40-watt mains light bulb. The design worked very well. The design basic was then modified by the additional of 2 additional pick-up coils, as shown here in this diagram. These are the 2 extra coils, and they're triggered at the same time by the passing magnets. That happens 5 times per rotation. The electrical energy produced in all 3 coils is passed to the 4 blue diodes to produce a DC power supply, which is used to charge battery A, which powers the circuit. That additional input to the drive battery, caused by the addition of these 2 extra drive coils, makes the system operate securely as self-powered and maintaining the voltage of battery A indefinitely. The only moving part of this system is the rotor, which is 110 millimeters in diameter and 25 millimeter thick, acrylic disc mounted on a bearing taken from an old computer hard disk drive. The arrangement is shown here in this photograph. The magnets are sets of 9 circular ferrite magnets, each 20 millimeters in diameter and 3 millimeters thick, making each stack of magnets 27 millimeters long and 20 millimeters in diameter. The magnet stacks are positioned so that their north poles face outwards. When the magnets have been installed, the rotor is placed inside a strip of plastic pipe which prevents the magnets escaping. If this disc is spun very rapidly, there's always a strong tendency for any magnets that are merely stuck to it to break free and become projectiles, which can be quite dangerous. But the plastic pipe here prevents that, and it's secured to the rotor using 5 bolts with countersunk heads. You can see the 2 of the bolts there. The spools of the stator coils are 80 millimeters long, and the coil flanges are 72 millimeters in diameter. The center shaft of each coil is made of a length of plastic pipe with a 20 millimeter outer diameter and an inner diameter of 16 millimeters, which gives a wall thickness of 2 millimeters. After being wound, that inner diameter is filled with a series of welding rods with their welding coating removed, and they are then encased in polyester resin, although a solid bar of soft iron is a good alternative. This is the circuit then, the basic circuit, with 3 batteries which are being recharged, 2 batteries which are being maintained, and the rotor which spins, and the transistor which drives it. With this coil arrangement, the prototype has run continuously for 3 weeks solid, maintaining the drive battery at 12.7 volts all of the time. At the end of the 3 weeks, which is 500 hours, the system was stopped so that it could be altered and tested with a new configuration. In the configuration shown above, the current flowing from the driving battery into the circuit is 70 milliamps, which at 12.7 volts is an input power of 0.89 watts. The output power is either 40 watts or close to it, which is a coefficient of performance of 45, not counting the fact that 3 additional 12-volt batteries are being charged at the same time, and that's very impressive performance for the circuit. The coefficient of performance is taken and calculated by taking the output power and dividing it by the input power which the user has to supply, which in this case is 0.89 watts. The drive method has been used so often by John Bedini that the developer tried to try out John's method of tuning for maximum performance. However, it was eventually found that a Hall effect semiconductor exactly aligned with a magnet gives much better results. Further development of the circuit continued, and the power output then reached 60 watts. This is impressive for such a small device, especially when you consider that there's no practical input, in that the drive battery is always being recharged. For this next step, the number of batteries has been reduced to just 1, and here is the circuit. The circuit is pretty much the same as before. You've got a triple winding there. You've got pickup coils which are fed back to the system which runs it, which is effectively this 100 microfarad capacitor. The 12-volt battery, which is also being fed power from the transistor and the coils that are driven by the transistor, is fed into an inverter, an ordinary 12 to 220 volt inverter, which is used to power a 60 watt bulb. It's also used to power a nominal 30 volt step-down transformer. That produces 42 volts because of the effect of the sine wave being rectified by a single diode, and this is a very effective method of dealing with the circuit. In this arrangement, coil B is also pulsed by the transistor and is now directed to the output inverter. The next advance was a circuit arrangement using a Hall effect sensor and an FET transistor. The Hall effect sensor is aligned directly with the magnets. That is, the sensor is positioned between one of the coils and the rotor magnet. There is a 1 mm clearance between the sensor and the rotor, and the arrangement is adjustable, so the sensor can be moved to its optimum position. The Hall effect sensor is an A3144E type, and the circuit has 150 watts continuous output, and it uses three 12 volt batteries. The first two batteries are used. One is used to power the circuit and provide a mains output. The second one is being recharged through three diodes wired in parallel to improve the charging current flow. The two-pole two-way changeover switch, marked as RL1 here, swaps the batteries over every few minutes using the circuit shown below. This technique keeps both batteries fully charged. Batteries charge better if they're not driving a load while being charged, so that's why the switchover is being done every few minutes. The Hall effect sensor drives a transistor. The transistor in this case was chosen to be a C5353 transistor, but any fast switching transistor such as a BC109 or a 2N2222 transistor can be used. You will notice that all of the coils are now being driven by the IRF840 field effect transistor. The relay used for the switching is a latching type, such as this one here. It's driven by a low current draw ICL555N timer, like this. The ILC555N timer is a very low current version of the standard 555 chip. Capacitors shown in blue here are chosen to operate the actual physical relay which is being used in the circuit. They're typically about 100 microfarads. The voltage needn't be more than 16 volts. They give the relay a brief switching pulse when the 555 timer changes state, which is every 5 minutes or so. The 18K resistors across the capacitors are there to bleed off the capacitor charge during the 5 minutes when the timer is in its alternative state. Typically a 100 microfarad capacitor works well, giving the latching relay a brief switchover pulse. However, if you wish to avoid switching between batteries, the circuit can be arranged this way, which is just straightforward without any additional battery switching, just two batteries in total. And while the coils are shown in this circuit diagram as being lined up, they are physically placed around the actual rotor. The 1N5408 diode, which is used to feed power back to the batteries, is a 100 volt 3 amp type diode. The diodes in the circuit diagram, which aren't shown with any type number, can be pretty much any of the diodes in the 1N whatever number range of diodes, the highest being 1N4007 for the enormously high price of 3 pence, can sustain 1000 amps, and it will carry 1 amp of current. The 3-strand twisted wire coil was used for both drive and output purposes. It's no longer necessary to use a coil of that type, and an ordinary helically wound coil of say 1500 grams of 0.71mm diameter enamelled copper wire would have been just as effective. Development continued, and the following circuit has been found to work very well indeed. In this version of the circuit, a 12-volt non-latching relay is used. The relay normally draws 100 milliamps at 12 volts, but a 75 ohm or 100 ohm resistor in series lowers that current to about 60 milliamps. That current is only drawn for half the time, as the relay is not powered up when the normally closed contacts are being used. The system powers itself very satisfactorily as before. However, the South African developer would very much like to omit the mains inverter, and so he prefers the following arrangement. In this version, the power circuitry is supplied by a DC to DC converter. There are lots of these very small, very cheap converters available on the market, typically through eBay. It gives additional voltage, the IRF 840, which drives the rotor and produces feedback power, which is distributed between the two batteries which are used to power the load. The developer stresses that the circuit operates in a non-intuitive way. First, the performance is somewhat reduced if the rotor spins faster, which is something which is not at all obvious. Then it has been found that using ferrite magnets produces a better performance than using stronger neodymium magnets. He sees it as the coil pulses being a mechanism for preventing cogging or backward drag on the passing rotor magnets. This is the same thing that Robert Adams found with his high-performance motor generator. In Robert's design, the rotor was drawn to the iron cores of its coils, making the motor essentially a permanent magnet motor. Admittedly, Robert's rotor got additional thrusts from the current in his output coils being switched off at exactly the correct instant, but that involved a somewhat higher level of design complexity. While there's no official claim that this South African design is actually a permanent magnet motor generator, it's difficult not to see that some of its performance will be coming directly from the magnets themselves. Finally, the design which the designer likes best of all is this one, which has no inverter or converter and which can power any ordinary 12-volt load. There are a lot of coils, a lot of magnets in the rotor, and apart from that everything else is the same. It's a neat design that works well and provides 12-volt output for any of the typical 12-volt loads. It's essential that the rotor is made very accurately and that there's no imbalance, and so no vibration forces are generated by the rotation. The developer uses a lathe to produce a perfect rotor, but that option is not generally available to most people. The larger the rotor, the more accurate it needs to be to avoid vibration when it rotates. If you have access to a 3D printer, a good rotor can be printed. One replicator shows his rotor like this, though admittedly he's using neodymium magnets here, whereas ferrite magnets would be preferable. The rotor is made in two halves and then bolted together. The developer has continued advancing his design. One of the things which he didn't like was the fact that the 5 coils being used required a total of some 1,640 meters of wire, so smaller coils were constructed. This new arrangement works spectacularly well, and each new coil has a total wire length of just 22 meters, which is less than 1/12 of the previous wire length. The wire size remains at 0.711 millimeters diameter, which is standard wire gauge 22 or American wire gauge 21. and each new coil is wound on a 6 mm diameter iron bolt core, and the windings cover a length of 24 mm along the bolt, which is two 30 mm diameter flanges mounted on it, giving an overall length of 30 mm, and the completed winding is 27 mm in diameter. There are 12 layers of the 0.71 mm diameter wire on each coil. These new coils are connected in two groups of 5, giving a DC resistance of about 4 ohms for each chain of 5 coils. The voltage spikes generated when a set of 5 coils is switched off is more than 500 volts. The wire in each coil weighs 70 grams, and the coils individually look like this here. They're also drawn like this, and the two sets of 5 coils in series are connected in opposite directions as shown above. The start of the set of the coils is shown in blue, and the finish of the set of coils is shown in red. This causes the current flow in opposite directions in each set of 5 coils. So one coil will have a north pole facing the rotor, and the coil halfway between it and the next magnet will have a south pole facing the rotor. The south pole attracts the rotor magnet towards it. The north pole pushes the rotor magnet away, and combined they work very well together. All 10 coils are pulsed at the same instant, and that instant is arranged so that one coil will be exactly facing a rotor magnet, and the other coils will be halfway in between. The developer now uses a different method of mounting the 10 coils, so there's more space to access the Hall effect sensors for adjustment. The whole top wood and acrylic mounting ring is easily removed by just loosening 4 screws. The small coils are held in place with cable ties, and they individually are easy to remove. Each coil has a resistance of 0.8 ohms, and the cores are standard 6 mm diameter galvanized iron bolts, not steel but iron bolts. They don't retain magnetism, that is, they don't become permanent magnets no matter how often they are stroked repeatedly with a strong permanent magnet. The set of 10 coils is mounted around the rotor like this, which is a very neat arrangement. Remember that the coils are mounted on their own support ring, and so can be handled as a single unit, which is very convenient. In this particular picture, the matchbox here on the right gives you a good visual idea of the size of the unit itself. It's a tabletop unit which is not particularly large. The working space underneath the rotor is greater than was available in the earlier designs. It's important to understand that the 110 mm diameter rotor has 5 magnets located even intervals around its circuit circumference. There are now 10 coils on the surrounding stator, and there are now 10 pulses per revolution. These pulses are powerful, and the current is cut off, and when that happens, each chain of 5 coils generates 600 volt spikes, although on occasion that can get up to as high as 900 volts. In this latest design, every second coil is wired in reverse so that it presents a south pole to the rotor magnet, and there are now 2 Hall effect sensors, one just below the rotor magnet and one just after the rotor magnet. This allows a simplified circuit with just one drive transistor, which is shown like this. This is the actual circuit here. This works extremely well, but the designer actually prefers this circuit, which has the 10 coils driven with the circuitry as before, but the two sensors are fed directly into a single transistor which pulses the field effect transistor itself. As it stands, that circuit runs very nicely, and it can charge 12 volt or 24 volt batteries, or power a 12 volt inverter connected across a 12 volt battery, or a 24 volt inverter connected across a 24 volt battery. However, the designer says, my preferred depiction of the wiring is like the drawing below, and it shows the wiring as it is actually lies physically around the coils on the device itself, and it is, I feel, easier to understand than when it is portrayed diagrammatically. This is the circuit diagram the way the designer prefers to see it shown. The winding wire comes in at the core for the start of the winding, and it exits at the outside edge of the coil for the exit or finish of the particular winding. And this is the way that they're connected. The finish comes through to the start, which comes through to the finish, which comes through to the start, and so on in a chain of 5, which are driven by the field effect transistor. In the case of the other ones, the feed is coming initially in through here to the start of the winding shown in blue, and out to through the finish to the start of the next one, out to the finish to the start of the next one, and so on, giving you two chains of 5 coils interconnected, and the arrows show the direction of flow of the current through the coils. This shows clearly the direction of the current flow through the two different sets. It doesn't matter if there are an equal or an odd number of magnets in the rotor, as long as there are twice as many coils. This is necessary so that there will always be one set of coils aligned with the magnets, and a second set of coils, where the current is flowing in the reverse direction, lying at the time of pulsing in between the magnets. Perhaps what might be helpful is to describe the process of optimizing the placement of the sensors. He says, I will describe the setting up of the two sensors, or perhaps I should say, he says, I will describe first the setting up of two sensors. Some points to pay attention to is the sensors must be mounted around the rotor in semicircular slots so that they can be adjusted radially, that's in and out. They also need to be mounted so that they can be adjusted vertically or axially. My sensors, for ease of setting up, each have an on-off switch. This makes it easier to monitor the functioning of each sensor individually at any time. Pay no attention to where the sensors are shown diagrammatically. Their optimum positions need to be found empirically and not by calculation. So step 1, switch off one of the sensors. Start the rotation and fire up the circuit. Move the first sensor radially into the position which gives maximum rotation. Step 2. Note the spin direction, clockwise or anti-clockwise, and maintain this direction in all subsequent settings. The rotor can be made to spin in either direction, but the timing of the triggering will only be correct in the direction of rotation which was used when doing the original setting. Step 3. Adjust the vertical height or axial position of the sensors to get the best spin or the minimum current draw. Step 4. You switch on the second sensor and adjust its radial position for maximum speed of rotation. Step 5. If you have installed 4 sensors, as I have, he says, then repeat steps 1 to 4. It's essential to understand what's happening as the rotor magnets move round past the coils and their associated cores. When the first sensor triggers the first set of coils on, in line with the magnets, the associated cores become north poles, and they repel the magnets past which they have just coasted due to their momentum. This enhances the spin. At the same time, the coils in between the magnets have also been pulsed, but the current flowing in them is in the reverse direction. This makes their cores south poles, which attracts the advancing magnets, reinforcing the spin yet again. Then the current switches off, and both coils lose their charge and coast into position the rotor coasts into position for the next cycle. Another aspect to understand is that one set of sensors fires slightly before or at the exact position of a radial alignment, and the second set fires slightly later when the first pulse current is switching off or dying. This provides an extra cycle and boosts the rotation. This may be easily proved by switching the sensors on and off experimentally, and it will be evident that each sensor is positively contributing to the rotation. I must stress that these optimum positions are best found by trial and error, and not by calculation or theory. Calculation may be intellectually satisfying, but it wastes an awful lot of time, as the intricacies of these processes are so little understood by us at this stage. For interest, he says, I have included the full circuit which I am using to run my Wi-Fi. And this is the entire circuit. This board here is the battery switching arrangement, and this circuit here drives one set of coils, and this arrangement here, this set of circuitry, drives the other set of coils. The output is fed to the batteries, and the actual load, which is a Wi-Fi system, is powered by this particular battery set here. Our thanks are again due to the designer for sharing his expertise and experiences so freely.